Okay, so let's continue. So today we'll try to finish this chapter 1 about invariant measures and probably start chapter 2. So we're on, today is our lecture number 4. So 29th August 2022. And so we are still on chapter 1, which is about invariant measures. Let me start maybe by recalling what we have been doing so far. So remember, we have our measure space M. M is, so think of M as a topological space. It is R, Rn, or manifolds in general. And we have our Borel sigma algebra. So the sigma algebra you get from this topology. And we have a measure mu. In general, think of this as something like Lebesgue measure, Dirac deltas, and so on. And we have F that is measurable, at least. So this is the least requirement we have. And remember, we define that mu F invariant if and only if we have F star mu equals mu. F star is a push-forward operator that acts on the space of measures. So last week we have seen an exercise. I've given an exercise to prove that this is a measure. And yeah, and remember we have seen the Perron-Frobenius operator. So Perron-Frobenius operator. So this is an operator that that acts on the space of densities. So for this, you're given M as a reference measure. M is a reference measure. And then you define if P, F, C, if C is invariant by this operator, then d mu, which is phi dm, is F invariant. Remember, by the definition of this operator, this was useful for expanding maps. Okay? Remember, we use this to find that Lebesgue is invariant for this guy. I said last time you don't need to use this operator, but as an exercise, it was good to see that Lebesgue is invariant for kx mod 1, which is a decimal expansion. And remember also the fraction expansion, which is given by the Gauss map. X gives 1 over x mod 1. And remember, d mu equals log 2 over 1 plus x dx is G invariant. Okay? And also we have seen the circle rotation, where we have Lebesgue is invariant. This is a translation, so Lebesgue is F invariant. And also we have seen that if the rotational angle is rational, every orbit is periodic. If it is irrational, every orbit is dense. So today we will do more like examples about flows, like continuous time dynamical system. So today we will talk about conservative flows. Okay, so let V be a smooth vector field on Rn. Let's say on Rn. I do this on Rn. Okay, by V smooth. When I say smooth, usually I mean C infinity, okay? So see that V can be written in coordinates. I'm on the Euclidean space, so I have the usual coordinate V, x1, V1, xn, Vn, x1, xn. So where Vi from Rn to R is a smooth function. Okay? Right? And so V is a smooth function, smooth vector field, so the components. So if you are also on general manifolds, everything holds, you can write your vector in local coordinates where the coefficients are smooth, okay? So this is, so given x naught, so I write it like this, x naught, which is x1, 0, and xn 0 on Rn, you can think of solving this ODE dx over dt equals Vx, and x at t equals 0 equals x0 here. So the solution of this ODE, okay, so I'm assuming that we know this guy has a unique solution because you have the existence theorem, and V is a smooth vector field. So we can talk about the solution. The solution is unique. The solution of ODE defines a curve through x naught tangent to V. So this is what I'm saying. So this means that your x naught here, this is x naught, and the vector V is tangent to x naught everywhere. Okay? So we said a V here defines definition. V defines a flow Ft by Ft of x naught equals so let's call the solution of AD defines a curve. Let's call this curve a name. So this is x naught. Oops, defines a curve. So sorry. So this curve, it depends on x naught, and the argument it takes is time. A curve through x naught tangent to V. Okay, tangent everywhere to V. This guy is x t x naught. So this point here, if this guy here is x t x naught, so this guy is the same as ft x naught. So this is the definition of the flow. So a remark or an observation is that for every t in R, for every t, ft is a diffeomorphism, is a smooth diffeomorphism. FT defining a smooth diffeomorphism. So remember from last lecture, we have seen that if you have a diffeomorphism, it preserves the volume measure if and only if the determinant is 1. So recall that FT preserves volume or Lebesgue. You know, sometimes I say volume, sometimes I say Lebesgue. So by Lebesgue, I mean here is dx1 until dxn. Sometimes you call it volume. It's just the Lebesgue measure you get from the structure in general manifolds. Okay? FT preserves volume if and only volume, if and only if the determinant of dft at x equals 1 for all x. Okay. But usually, you know, this condition on the determinant is not easy to check in general. It's not easy to check. But thanks to Louisville Formula, you can express this as a divergence of the vector field. So there's Louisville Formula that tells you that the determinant of dft x is exponential integral from 0 to t of the divergence of the vector v along the orbit until time t, fsx ds, where here divergence of v is just dv over dx1 plus dv over dxn. So from this you have the Louisville Theorem that you can guess. So F preserves the flow, Ft preserves volume if and only if divergence of V is 0, is identical to 0. So this is called divergence free. Okay, divergence free. Okay, so for flows, this is one way to see if the flow preserves Lebesgue. So there's this exercise actually which is interesting to check. So this is about Hamiltonian flows preserves, you know, the volume measure. So exercise, let U be a subset of R2n and H is from R2n, from U to R is a C2 function. So let V from U to R2n be the vector field. So V, so here I'm using the coordinates P and Q, P1, Pn, Q1, Qn. So these are the usual coordinates that people they use on the tangent on the cotangent bundle to define the Hamiltonian. Okay, so this is dH over dQ1, dH over dQn, and minus dH over dP1 minus dH over dPn. So show that the vector field, the flow, so it's called Hamiltonian flow because it comes from Hamiltonian function, so the vector field is given by Hamiltonian function. Hamiltonian flow given by V preserves Lebesgue. Lebesgue, which is M, is dP1, dPn, dQ1, dQn. So usually people they just write dP, dQ for this notation. Yeah. Actually, there is another more geometric way to define this, which is from the geodesic flow that I will just talk about it a little bit, and if somebody is interested, that could be a good project, a part of a project to present the presentation at the end of the lecture, at the end of this course. All right, so yeah, so this is Louisville Theorem that gives you, some necessary and sufficient condition for the vector field to be, for the flow to preserve Lebesgue. But in general, Lebesgue is not the only measure that flow must preserve. Sometimes they preserve other measure that is maybe absolutely continuous with respect to Lebesgue. So it's good to have another criterion here that's not only like volume, like preserves volume. So for that, I would like to introduce another definition. So definition. So the lead derivative, this is the definition I'm going to give, is the lead derivative of a form. Lead derivative. So let M be a measure, be a smooth measure. So usually when I say here a smooth measure, we know Lebesgue is smooth because it comes from the usual coordinates, which we know they are smooth. But another smooth measure is just it can be seen as a multiplication by a smooth function of dx1, dxn. That also defines a smooth measure. So it's in some cases it's good to see these measures as like top forms, like n forms, n differential forms. So so here, when we write here, where did I say it? Somewhere here. So here the Lebesgue measure M, you can see it as dx1, dx2 wedge, dxn. So this is a top form here because it is n dimension, and usually it's good to look at measures as top forms. Like form is just something that acts linearly on the tangent bundle. But if you don't know that, don't worry, it's not a problem. We don't need to worry too much. So the lead derivative, and let M be a, and V be a smooth vector field. So the lead derivative of M by V is, so this is a definition. So we write LVM to mean d over dt at t equals 0 of ft star m. So I will say what are the quantities here. So F is the flow given by V. Ft is the flow given by V. So by the way, this is something that is not said in the book, but it's good to know. It's good to know. And by this is a pullback. You can just see that Ft star, and so this Ft star m, if you apply to, when I said it's good to see this as an n form, if you apply this to some vectors, some, n vectors, so this is m at dft, apply to what you had here. So so it's good to see like smooth measure as just stop forms on the space. In the pullback of this form is defined like this. In terms of measures, it's also good to see that a measure, this is just the measure of the image Ft of a set A. Okay? If you put here, if you see, so this is equality when you see M as a top form, okay, as a top differential form here. But if you see just, if you look at M as measure, you should put here a set A, and this will be just Ft of A. Okay? So there's this lemma that tells you that Ft preserves M if and only if the lead derivative of Vm is 0. So, sorry, I should be maybe more gentle here. So this as forms. So, but as like measures, you should see Ft star. So let me just open here a small bracket that Ft star M of A, this is M of Fta, okay? And you want to look at them as measures. And you look at Ft M as like a measure acting on sets, but this is the infinitesimal version. This is an infinitesimal version of this. Okay? Because remember, like look, when you write a measure of a set, A is dmx. When you do this, so this quantity is an infinitesimal version of the measure. This is what you integrate. So when you do it infinitesimally, that will involve the differential. When you do it with one form, with sets, this is what it means. Okay? Yep. So, yeah, this is This is a characterization of invariance. So the proof of this is actually easy, because is ft, so this way here, to prove this, you just look at what is LVM, is the limit when epsilon goes to 0 of 1 over epsilon f epsilon star m minus m. This is just the definition of the Lie derivative. Okay. And ft preserves m, it means that this is 0. Because remember that ft is a diffeomorphism. So invariance of f and invariance of f minus 1, they are the same. So this guy, ft, preserves m, and being diffeom implies that ft star of m equals m for all t. So this is 0. This is 0, sorry. This is 0. Then LVM is 0. So the other way is just using a type of fundamental theorem of calculus that you can do here. You can write f epsilon star m, or ft star m minus m as the integral from 0 to t of fs star of lz m. Mm-hmm.
This smooth measure that you are talking about, you are defining this measure with the Riemannian metric behind. Yeah.
So when I say smooth measure, yeah, it was.
You can take a Lie derivative.
Yeah, of any other form. Yeah, no problem. Yeah. So this doesn't just reduce to top form. For any one form, you can consider the Lie derivative, because this, where is a definition? This definition, this doesn't see when m is a top form or not. Because I don't know how much we know about differential forms and stuff. That's why I just do it for the measure, for the top form. Yeah. So, yeah, the Lie derivative is defined for any form, but here we are just interested on top forms, which defines measures. This is also something that you can check it is true. So to prove this type of equalities, so if you suppose that this guy is a form, you do it for 0 form, which are function, and if you check it for 0 forms, you just have the generalization for general forms. Okay, so this is just type of fundamental theorem of calculus for differential forms. This is just fundamental theorem, because this is a derivative, and this is the function at t minus the function at 0. It's a type of fundamental theorem of calculus. Okay, but if you don't know it, it's not a problem. This is the I just want to do this, add this part to the course, which is not in the book, because it gives another way to see, to characterize invariant measures like this. Mm-hmm.
Do you have a Louisville formula for the Lie derivative?
Sorry?
Do you have a Louisville formula for this general case of the Lie derivative?
Louisville formula. For the Lie derivative. A way to check it, like a formula like divergence or. No, there's no. No, there's no formula. I mean, this depends really on the vector field and stuff, and it doesn't use anything like determinant or No. Yeah. So, so this guy being identical is 0, it gives that this is 0 for every t. Yeah, because if you don't know about differential forms, it's difficult for me to go to the, to write all the details of this proof. But if you don't know it, you can just look at any textbook and you can see it. So to check this, you just do it for 0 forms, and it works for all guys. Okay. Yeah. And there is this nice exercise that I like very much. I have been giving it for the last 3 years in this course. So there is this exercise. So you take V, be smooth vector field. So I did not talk about manifolds, but everything I'm saying here, they also holds on manifolds. You do coordinates. Be a smooth vector field. And phi, and so ft be the associated flow. Associated flow. So whenever I say associated flow, I mean the flow defined like this, okay? So let C be a smooth vector field on Rn on U, so, on an open set of Rn. Phi from U to 0 plus infinity be smooth functions, or C1 functions. And so we write V phi equals V over phi is a vector field. This is just a reparametrization of the flow. And ft phi be associated flow, the associated flow. So this is the flow associated to this vector field. Okay, I have two vector fields, two flows, but see that here the flow lines are the same. You just speed up or slow down depending on C here. So the flow lines are the same. So in this example, for this exercise, if this point is ft x naught, this guy is f phi another t prime x naught, where t prime is the function that depends on c and x naught. Okay, you don't change the flow lines, you just reparameterize it. This might go faster in case of c is less than 1. In between 0 and 1, you are speeding up, or it is slowing down the flow, like you divide by something big, you slow it down. Like for time 1, f, the original flow can be here, but for time 1, the previous one can be here, depending on phi, okay? So this is what these two flows are. So here, ft preserves a volume measure M, a volume M, if and only if ft phi preserves M times phi, preserve the volume measure. m phi, which is phi times m. This is a nice exercise to check about reparameterization of flow. So if you have a flow, you do a reparameterization, they preserves measures that are absolutely continuous with respect to each other. Like they just differ by a function. Okay. So probably I'm gonna tell us to do this exercise for you during the problem session. So I will define two examples of flows. One is, so example one is called a suspension flow. So suspension flow, so we suppose that let M be a topological space. But first of all, what this is about, so this is about defining a flow, a continuous system from a discrete one. From a discrete one. Remember, from the first lecture, we know that if you have a flow, the flow contains is a continuous dynamical system. It contains a discrete time dynamical system. And we are supposed to know an example where you cannot embed, there is a discrete system that you cannot embed into a flow. Okay? Now, this is now trying to solve the problem in another way. Like you give me a discrete system, can I construct a flow from it? So the way we do it here, we go to another space. We increase the dimension of our space to 1, and there we can do it. So let M be a topological space and F from M to M. I suppose this is continuous, okay? I don't want to do crazy. Crazy stuff. Be continuous. And let R from M to 0 infinity be a, R here is a continuous function. So this is usually called a roof function. We will see why it is called a roof function. So from M, from M, F, R, we define the following space. So this is M, F, R, which is M times R with an identification. So X, Rx is identified with X, F of X, sorry, and 0. It's good to draw a picture for this. So let's say I have my space M. Let's think of it as like the interval. I have a roof function. So this is R, which is a roof function, the graph of, okay? So if I take this point here, so let's suppose that I have here, okay, this is 0, 1, okay, which is our M. So M is 0, 1 here. So, and then I have a function, okay? It can be anything. It can be 2x mod 1. It can be any dynamical system. Okay, 2x mod 1 is not continuous. Yeah, it's not continuous, yes. Yeah, depending. So, on how you do with 0, 1. Anyway, so we have a continuous map. So what is this map, this manifold doing? So this space is a two-dimensional space, right? It has two dimensions, 1 and 1 in this example. So what do? You take this point here. This point is x at x, right? This point is x here. What do? You identify this point with. So this is, let's say, f of x. So this is x is 0, okay? X, and this is 0, okay? So this will be f of x is 0. So you identify these 2 points. So this is how this space is defined. So if you have any other type of manifold also, you can think of having a roof function. So if this is your point xy, see that this is xy 0, and this is xy r of x. This point is identified. So this point is mapped to f of xy 0. So this point and this point are the same. You do this identification. Before that, a question that you might ask, whether this defines a topological space or like a manifold. So this is a topological manifold. So I will not ask you to do a proof of this, but if you want, you can find it. There's a way to, you can do some coordinates to find. Okay, so I'm halfway, okay. So this is a fact. I won't ask you to prove it. If you know how to prove it, it's okay, but MFR is a topological manifold. And what is the flow now doing? The flow, F tilde, the suspension flow, definition, the suspension flow from F with roof function R is, so let me find the notation. Yep. So is this flow is Ft that is defined from MFR to MFR, that is Ft of xs. So this space has two coordinates. There is the coordinate on the base space and the value for S, which is on the real line here, number. So this guy is x t plus s. So this is just a vertical flow. So this is just a flow that goes vertically. When it hits this point, it is identified with us. So you keep going, and then, yeah. So what is the relationship between this flow ft and f, the map that we started with? So see that f is nothing but the first return time map. So f, so remark, f is the first return map of the flow ft to M. Okay, to M. I have the base space. F is just the return map to this space. If you're familiar with global sections, like sections of the flow, this M is nothing but just a cross section for the flow. A cross section is just like a codimension 1 space where every flow line hits. Now, okay, this was just to define what you have. So this is a suspension flow. This is how it is defined. Whenever you have a dynamical system, you can define the corresponding suspension guy. What do I want to say now? I want to say, okay, that's not what I want to say. Okay, I was here. Yes, so you can define a measure. If you have a measure for F, you can define a measure for the flow, okay? So, definition. So, if mu is a measure on M, you can define a measure on this by, so then we can define a measure nu on MFR on this space, which is dimension +1, dimension of M +1. That is defined by nu of E times I is just nu of E. Okay. So we're here, sorry, mu, yes. Where E is in B, which is the border sigma algebra on M, and I is an interval. Because this set, E times I, this set generates the Borel sigma algebra on M times, on MFR, sorry, on this space. And you can check that if mu is F invariant, then So check that. If mu, it's not, actually there's nothing to check, it's just a remark. If mu is F invariant, then nu is Ft invariant. So from a discrete time dynamical system, there's a way to find a continuous one by increasing the dimension of the space, and any measure you can lift it to a measure on this quotient space. So this is called a quotient space, okay? So exercise. So are there Ft invariant measures that do not project to an F invariant measure? Yep. Okay, so let me see how I'm doing this time. Okay, I should speed a little bit up. So this is one example of continuous time dynamical system, suspension, flow. And there is another example, which is the geodesic flow. Example 2. Geodesic flow. So this is a subject that I will not do much about because I'm assuming that many people here, they don't have the background, the geometric background to understand all the details. So I will just explain it briefly, and if someone is interested, there's a possibility to do part of a presentation at the end of the lecture about this, okay? About the invariant measure for the geodesic flows and so on, okay? So if you suppose that let M, G be a Riemannian, a complete Riemannian manifold. So G is a Riemannian metric. So yeah, so if you haven't done courses on Riemannian geometry, this you don't need to worry too much about it. So I'm just presenting it in case somebody is interested. By the end of this, we can have a presentation on this. So this is a metric, a Riemannian metric. A metric is just, something that acts on. So you have Gx to R, with the properties that we know. So the geodesic flow, flow Ft is a flow that is acting on the tangent bundle. So if you want, so you can take the definition where you restrict just to a unit tangent bundle at a, at the energy level being 1, okay? So this is how this flow is defined. So let's say I have my manifold that can be something like this. So this is a surface. So Tm is 4-dimensional. When M is dimension 2, Tm is the tangent bundle, which is 2n-dimensional. So if you don't know about this, don't worry. There's no... So I'm just saying it here, so if somebody is interested, we can do some nice presentations about ergodicity of some measures. So what are points on the tangent bundle? So V is in Tm. That means that V has a foot point and given a vector on the tangent space. So you have this V is given by a point that is P on the surface and the tangent vector. And FTV is just taking the geodesic. So this guy here will be FTV, where this curve here is the geodesic starting at V in a time t. Let me write it somewhere here. So FTV is the tangent vector of the geodesic, tangent vector at time t of the geodesic. Oh, by the way, sorry, I need to restrict myself to unit tangent bundle, like unit speed geodesic. So this is T1, which is just the set of vectors of norm 1, okay? Because here there is a problem of parameterization. So is a tangent vector at time t of the unit speed geodesic starting at V. You give me a vector, I draw the geodesic through this vector, and at time t, that is FTV. Okay? And there is a so-called Louisville measure. So definition. So let E be a subset of T1M. So what is this space T1M? Is like you have this is M. So at every point here, you attach a sphere. So this is what T1M looks like. So this whole thing is T1M. So if you have a subset of T1M, it makes sense to write it as U and EX here, where at every point here, I define the subset I take from this circle, from this sphere in higher dimension. So where this guy is a subset of TXM, and this guy is a subset of M. Okay, so the Louisville measure, there are many ways to define it. I'm just giving one here. So the Louisville measure M of E is given by the integral along U, the integral along EX of d lambda d volume X, where here d lambda is Lebesgue measure on TXM, and then d vol is the Lebesgue measure on M. On M. So last year when I was giving this lecture, I took maybe a couple of lectures to do a geometric proof of the invariance of this by the geodesic flow. But I think I won't do it here because it requires a lot of geometry background that I'm not, asking people to have that. But if someone is interested, we can see a presentation theorem. M is invariant by if Ft invariant, where Ft is a geodesic flow. So again, this is not something I'm supposing that you all know how to do, but if you just actually it is one can prove this actually. One can prove it using the exercise I wrote here about the Hamiltonian flow leaving invariant the volume measure, because the geodesic flow, you can see it as a Hamiltonian flow, and then you can use that exercises. You can find that the Hamiltonian function is just given by the energy level, which is 1/2 of the norm of the vector. Yeah, there's one way to do it, as considering the geodesic flow, seeing the geodesic flow as a Hamiltonian flow, and using the exercise using divergence of this. There's another more geometric way, which requires some understanding about this map, about DFT, how this map is acting using Jacobi fields. But I'm not asking everybody to know that. So if someone is interested, there are some nice projects, presentation about the geodesic flow, about ergodicity, invariant measures, and stuff. So for this, I will not do anything more on this. I will just leave it like that. Okay. Yeah, I don't want to do that. So for the chapter 1, basically this is what I want it to do. Yeah, so this is chapter 1. Yeah, to do a brief overview of this chapter 1, remember we have this discrete time dynamical system. Some cases we know how to find invariant measures using, when you have expanding, the parent-Frobenius operator is a good way to find invariant measure. If you have periodic orbits, you can take Dirac deltas. This gives invariant measures. And also, for flows, you have ways to check it. So if you know the vector fields by hand, to check that volume is invariant, you can compute the divergence, Louisville Theorem. Or if you don't know the vector field by hand, but you know something else, you can see the Lie derivative, the Lie derivative, how this flow is moving the volume. That's the Lie derivative. Or you can see the parameterization, like the exercise I erased here. So now it's time to start chapter 2, which is about existence. Why do we what conditions are needed to have invariant measures in general? Okay. So chapter 2. This will not take a lot of, maybe by Wednesday we will close this chapter. Chapter 2 is about existence of invariant measures. So our goal here, the goal of this chapter, is to prove this theorem. So let F be a continuous map on a compact metric space. So then F has an invariant probability measure. Yeah, so see that this theorem that we will prove, it has conditions we did not have before in general. It's compact metric. So let's see some non-example or counterexample of this. If I take f from 0, 1 to 0, 1, x gives x over 2. Yeah, do we have an invariant measure here for this? No. Why?
Because you think exponential decay maybe.
Do we have an invariant measure here?
The existence of the invariant measures happens when you have a compact space.
Yes.
But not a compact.
Yeah, but I don't want to use this theorem, but I'm just saying that why this doesn't have an invariant measure. So, I mean, you can have, if I just do this, you would have an invariant measure, but it's not compact. Now, why this doesn't have an invariant measure? Or what is the first implication?
Take the preimage of just half the interval.
Mm-hmm.
Then it will have to be, it will be the whole interval. So it's a contradiction unless that one of them has measures in the direction.
Yeah, you find. But what measure are you using when you say that that's a problem?
Yeah, you suppose that there is an invariant measure here.
Yes.
And then you take the interval that goes to from zero, the whole interval. Maybe the interval that goes from 0 to 1/2. No.
I think what you are saying is correct, but one just needs to to set it properly. To say it properly, if you consider you have an invariant measure, this measure should be accumulating at 0 because of Poincare recurrence, for instance, because of Poincare recurrence. So suppose by contradiction, suppose mu is f invariant. So if I take a set E, which is a half 1, so points of E, they never come back to E by f. Okay? So that means that the measure of this set has to be 0. Okay? So the return time, if you want to row E, this guy is identically this. If I take this, the point, they never come back to E. So Poincare recurrence me of this set is 0. Because if it has positive measure, the point they come back. You can do it for any other interval. For any other interval that is a subset of this guy, unless it contains 0. Okay? So any...
So if you have a metric space that is not compact and you have a expanding map, a contracting map on this, you can never have a...
No, but it depends on the points where the contract is in the space or not. If that point is in the space, that point has to be a fixed point.
Yeah.
And if it's a fixed point, you take a Dirac delta at that point. So basically, so you keep going and you say that, you know, the only invariant measure would be the Dirac delta at 0. And that is not on our space. That is not part of our space.
But I'm so the measure would be identically 0.
The measure would be identically 0, yeah. Oh, yeah. Yeah, yeah.
In this case, because if you compactify the space and put measures 0 index extreme, so
Yeah. So this is...
So if you have a metric space that's not compact and a contracting map, the only measure that this map leaves invariant is a Dirac.
Yes.
To use the Poincare recurrence theorem, we need the hypothesis of the measure being finite. Couldn't we have an infinite measure that allows certain values to be infinite and it being invariant?
Yeah, that's a good question. So first of all, for this theorem, we talk about probability measure. We mean finite, okay?
Yeah.
But could we put something infinite here? I don't know. That I don't know. That's a good thing to think about.
I mean, if the
Yeah.
space has measure, any non-empty subset has measure infinite, I think it works. I'm not sure. But
what if it's sigma finite?
Yeah, I think if it is sigma finite, that might be still false. Yeah. Yeah, I don't know how to.
For infinite, the one that I think is that measure that counts the set. I mean, if you have a finite set,
Mhm.
the number could be but I don't know if it could work.
The number, sorry?
The countable set, I don't know how to say it in English. You can say a more simple thing with the measure which is maybe 0 only in the empty set and infinite elsewhere.
It's where, yeah, but
But in this, we want a sigma finite.
what if we had something like, if the subset contains a neighborhood of 0, if it has 0 and something is of infinite measure, and otherwise it has 0 measure?
yeah, that's the measure that I'm seeing. It's still a 0 measure on this space because that measure would be supported just at 0. Because it will be a 0 measure as, yeah, and if you put infinite everywhere, I mean, that's not a, yeah, that's not interesting. And it would be good to think of sigma finite, but I don't think we can have it. Anyway, so what we lack here is compact. So the only F invariant, there's no F invariant finite measure. There is no F invariant finite measure. So because we don't have compactness, fail. Compactness fail. Let's modify this a little bit by making it compact here. This example and see where we get. So let's suppose that we have f that is from 0, 1 to 0, 1. This guy is compact. And f of x is x over 2 if x is in 0, 1, and f of 0 is 1. F of 0 is 1. This is a kind of a ugly example. Do we have an invariant measure here? First of all, this we know that this is measurable. Okay, this is a measurable function. Do we have an invariant measure here?
I think you all had said this example in the previous lecture.
Sorry?
I think you have mentioned this example.
I did? Okay. I forgot, yeah. Do we have invariant measure here? Yes, it will be a Dirac delta here, but Dirac delta is not invariant here.
No, yeah, but I mean, it would have to be.
Yeah, and why do we have, why this theorem doesn't apply? So this is continuity here. Fails here. So I mean, let's go now to try to do the proof. Okay. In 10 minutes. In 10 minutes, what I would do, I would just do a sketch of the proof, of the general proof, and then on Wednesday we will do the complete. So sketch of the proof, just the general idea. So the first thing to do here is to first thing is to define a topology on the space of measures. On space of measures. We call it weak star topology. And this is a topology that we will define using, continuous bounded function. So let me just tell you the intuition behind this topology. So see that we have this fact. Two measures are the same if and only if, by definition, they agree on all Borel sets. Okay? So if and only if mu of E, the definition, okay? This is definition for all Borel. Okay. But this, you can write it as, the integral of phi d mu for all phi continuous bounded. Okay. When you have this, to have this, you just do the usual step function, simple functions, dominated convergence theorem, and the other way also. So the measure mu is uniquely determined by this data. So this data, so the integral of phi d mu, phi continuous bounded, uniquely determines the measure mu. So when we want to define a topology, we want to define, to make a meaning of two guys being nearby. So with this, we can think of two measures are nearby if they agree on a big class of function. Like if I can find 1 million of functions, such a functions, where their integrals are nearby. So that's the topology that we will define, which is called weak star topology. Okay, so the neighborhoods are just, if you fix mu, the neighborhood, you take a measure where there is big class of functions where the integral almost coincide. How small is this neighborhood is determined by how big is the class of function. So if I take 1,000 functions, the functions are nearby like this. If I add another 1,000 to that 1,000, there will be nearness. Okay? So that's how we will define the topology. And then we have this map F star from the space of measures which is continuous. So once we have a topology here, we can put a we can, check whether this map is continuous. And we need to check that the space of probability measure is compact and convex. Is compact and convex. So convexity, it's okay. So if you have probability measure, you take a convex combination, it will be again a probability measure. But being compact in this topology, that we will define, is something that requires some work. And once you have it compact, you have F star compact that is acting on a compact. So the space of probability measures, we call them usually M1M. So once you have it, it is compact. There is, the usual fixed point theorem that gives you. So F star M1 to M1 has a fixed point by, I think we will do, I always, get wrong the name, who shouted Tikhonov. Okay, it depends on who. So continuous. This guy being compact and convex, so you have Schauder. Tikhonov gives gives fixed point. There is also, this is one way to prove it. Okay, you define the topology, F star is continuous, the space of probability measure is convex and compact, Schauder Tikhonov. There's another alternative. We will also see this direct proof by averaging. So so in general, if you want to see something invariant in dynamics, to get something invariant, what we do is we average along an orbit. So you just start with pick any mu in the space of probability measures, and then you can define nu n, which is 1 over n, the sum of fi star mu I equals 0, n minus 1. This guy will be again on M1 because I'm normalizing here, and this guy is a probability measure, and this being compact, this will have an accumulation point. Of nu n defines an invariant measure. So this is a direct proof, just averaging. So probably on Wednesday we will finish this chapter and then go to the ergodic theorems. So I will stop here for today. I think Mateo said who would come to talk to you, but I haven't seen him. Yeah. Yeah, I stop here for today.